Good afternoon, everyone. Once again, welcome to day 4, second session, second half, not second session, second half. In second half, we have Professor Ivan Scutino as a speaker. Before he starts his session, let me introduce him. As such, he doesn't require any introduction. Still, I try to introduce him. Professor Coutinho is having 34 years of experience. He is basically PhD in technology. He is working since 1986 in Bombay College of Pharmacy, University of Mumbai. He is a professor of pharmacochemistry. His thrust area of research is NMR of peptide, quantum mechanical calculation, 3D QSR, homology modeling, docking and structure-based design. He also has some achievements and awards to his name. Few are like CIPLA Fellowship, then AICT Career Award for Young Teacher, Visiting Fellowship at University in USA, then in Punjab University also, UGC Research Award. He also has 2 patents on his name. He has more than 165 publication in high impact factor journals. More than 100 presentation he has delivered in various national and international conferences, symposia and seminar. Also more than 125 invited talks. He has also received about 200 lakhs of grant from various agencies like DST, DBT, CSIR, UGC, AICT, and some corporate pharma, both from India as well as abroad. With this brief intro, I request Professor Coutinho to start his session. Thank you, sir.
Thank you, Dr. Sandesh Loda, for that kind introduction. And I'll start sharing my screen.
Yes, sir. Slide is visible.
The screen is visible.
Yes, sir.
Okay, so this is a hard time to give a lecture in the afternoon, especially after a nice lunch. And I'm going to talk on something that is a little bit mathematical. So many of you all would like to sleep, I know, so just forgive me for that. Okay, so my talk is going to be centered about chemometrics. And what is chemometrics? I will just elaborate shortly. The whole idea is how to use chemometrics to make sense of databases. Okay, so chemical databases are basically the backbone of drug discovery and development. Now, these databases have a wealth of information, a wealth of knowledge, and we can now cull out the information, useful information to discover and design new drugs and also for drug development. So how do we extract that useful information from these databases in order to design and discover new drugs and also for drug development? My next slide lists some of these databases. Many of them are publicly available and they're quite familiar to many of you all. There is the PubChem, the Zinc database. The Zinc database today has several million compounds, which actually you can use for doing docking. Then there is the ChemMBL database, which has also about 1 million small drug-like molecules and associated with it about 8,200 drug targets. Then there is the NCI, ChemDB database, etc., etc. There are huge number of these databases. And some of these databases contain several millions of compounds. So there is a wealth of information, a huge amount of knowledge contained in all of these databases. But how do we extract the useful information? How do we glean from these databases that what is important in order to design and discover new drugs, new small molecule entities? Okay. One of the ways in doing this is basically chemometrics. So chemometrics, as defined here, is the science of extracting information from chemical databases with the intent of learning underlying patterns, relationships, and predicting new properties or behavior of interest. So we can use chemometrics essentially to understand relationships that are present between these molecules stored in these databases out there. We can segregate these databases into different classes. For example, we can segregate these databases into molecules which are active against a particular target and molecules which are inactive against a particular target out there. So you can segregate databases, you can classify databases, you can study patterns, okay? You can detect patterns, you can develop relationships, both qualitative relationships and quantitative relationships between the molecules and their endpoints. All of this is possible with chemometrics. And some of the tools in chemometrics are quite familiar to you. You're all familiar with regression. Then there is clustering, there is pattern recognition, etc., etc. So these are some of the various chemometric techniques. Okay, and I'm going to talk about a few of them. Principally, I'm going to concentrate on regression. Okay, before we talk about how do we understand relationships that are present in the molecules in the databases, and how do we develop models, okay, to relate the information that is there inside the database to some other information that is also contained in the database. Now, what do I mean? I mean by this. So there are molecules in these databases, and each molecule can be defined by a certain chemical characteristics, okay, or what we call as the descriptors for these molecules. These descriptors, I will label it as the X, okay. So molecules in a database can be described in terms of their chemical characteristics, and these chemical characteristics will include lipophilicity of the molecules, their electronic properties, their steric properties, that is the size and shape of the molecules, the topology of the molecules, how the atoms are connected to each other, and fingerprints, okay? Fingerprints are basically signatures of these molecules, just as our fingerprints are signatures and identities of each one of us. Just like we have a retina and a fingerprints that is now used to capture, okay, and identify us in airports, in malls, etc., etc., etc. out there. So likewise, molecules can also be described as by their fingerprints, that is characteristics for each molecule out here. Now, some of these descriptors or the chemical characteristics of these molecules, as I said, their lipophilicity, etc., etc., and they are described. For example, lipophilicity can be described in terms of the partition coefficient, can also be described in terms of the partition coefficient, which is calculated. This is experimentally measured. Okay, lipophilicity can be described by the distribution coefficient, can be described by solubility. Electronic properties of a molecule can be described by the energy of the lowest unoccupied molecular orbital, energy of the highest occupied molecular orbital, the hydrogen bonds, hydrogen acceptors and hydrogen donors, the electronegativity of the molecules, the dipole moment of the molecules, etc., etc. Coming down to the steric properties of a molecule, we can describe the steric properties in terms of the molecular weight, molecular volume, the Taft steric constant, the sterimol parameters, the 5 sterimol parameters labeled as L1, B1, B2, B3, B4, B5, and molar refractivity. And the other chemical characteristics are the polar surface area, the electrotopological state, the similarity indices, similarity scores, etc., etc. out there. Okay, so all the molecules in the database, we can describe them by these properties, which we label as descriptors, and we code them as X. So X will be log P, X can be log D, X can be HOMO, X can be LUMO, X can be molecular weight, etc., etc. Okay. Then in the databases also, you will also see that molecules are also characterized by their endpoints. Okay, so molecules will have associated with them pharmacodynamic attributes. Pharmacodynamic attributes could be like the activity of the molecules. Okay, so in the database, you'll have the activity of the molecules in terms of the IC50 value, the ED50 values, or the inhibition constant values. Or the molecules may also have associated with them pharmacokinetic properties like the volume of distribution, the clearance, the Cmax, the half-life, or the molecules may also have attributes like toxicity and metabolism out here. So these are called as the endpoints. Why? Why is the endpoint? So I want you to clearly understand what is X. X are the descriptors of the molecules in the database, and these are lipophilicity, electronic, steric, topological, connectivity, fingerprints, etc. And the endpoints are these pharmacodynamic, pharmacokinetic, toxicity, metabolism endpoint. But we are not only going to restrict to these biological endpoints for these molecules. They could also be physicochemical descriptors like the solubility of the molecules, the boiling point of the molecules, the chromatographic retention indices of the molecules, their solubility. Okay, and this is important, for example, to pharmaceutics people, drug loading and polymeric micelles, etc., out there. Okay, so we have two attributes of the molecules in our database. We have the Y attributes, which is all above, and the X attributes, which I've listed in the previous slide. These are the X attributes out here. And often we want to write a relationship between the Y endpoints and all of these attributes X. Okay, so that is the model we want to build. Okay, so we want to build a model between, for example, the activity, the IC50 value, and all these X descriptors for these molecules in the database. Or we want to develop a model for the distribution, volume of distribution for the VD and the descriptors of the molecules in the database. Or we may even want to build a model for the solubility of the molecules in terms of their descriptors. Or still important, maybe the drug loading on polymeric micelles. That is, we want to develop a model for the drug loading on polymeric micelles in terms of the descriptors, lipophilic, steric, electronic, etc., etc. So how do we do this? How do we develop such relationships? As I said, we are going to use the chemometric tools, and I told you one of the chemometric tools is basically regression. So the method in order to develop a relationship between the Y endpoints, any one of these endpoints that I've listed out here, and the descriptors that we have seen in the previous slide, is to use regression analysis out here. Okay, so this is regression. This is about regression analysis. For explaining to you regression analysis, let me consider why the endpoint which I'm going to model is biological data. And I said it could be anything. It could be pharmacokinetic, it could be physicochemical properties, it could be metabolic data, metabolism data, it could be toxicity data, it could be anything. But for this explanation, I'm going to restrict myself to Y being the biological data. And what is assumed that biological data that is often reported for the molecules in a database always contains some error. Okay, so here is the biological data that we often see for these molecules in the database is the Y observed. And I'm going to build a model between two descriptors. For example, this could be log P, and this could be by HE HOMO, the energy of the highest occupied molecular orbital out here. And this is the error that I was talking to you about out here. So the biological activity is often associated with the errors. Note that the descriptors X1 and X2 are believed not to contain any error. So there is an error only in the experimentally determined endpoint, okay, and not in the independent variables or the X descriptors out there. And what we want to do now, we want to model, okay, we want to model this endpoint, this activity endpoint by this equation. Okay, we want to calculate it by this equation, ax1 plus bx2 plus c. And remember that there is no error inside this out there. So our model, okay, must approach the observed y value as close as possible out here. So how do these two equations get as close as possible? The modeled value and the experimentally observed value, how do they become close to each other? If this error is equal to 0, if this error is equal to 0, then the calculated value will be as close to the experimentally observed value. The calculated value is the one that we are trying to model. Okay, so what does this mean now? Mathematically, it means that we are seeking in order to get the summation of the errors. Now, why the summation of the errors? Because when we do regression analysis, we do it for a data set of molecules out there. Okay, for that data set of molecules, maybe 30 molecules, maybe 40 molecules, maybe 50 molecules, 100 molecules, even could be 1,000, even could be lakhs of molecules out here. And that's why we have this summation out here. So for each one of these observations, remember there is an error. Okay, so if I have 30 observations for 30 molecules in my data set, all these 30 molecules, their endpoints will have some error out here. And therefore, I'm seeking to minimize the error for all the molecules out here, make it as small as possible. The target is to make it to 0, but it is an idealistic case where the summation of the square of the error will go to 0 out there. So how does the error go to 0? If I take the difference between the observed, okay, and the calculated, and I square this so that I make it a minimum, this is how the error will go to 0. I'm emphasizing this. What do I mean? That my model will now be as close to the observed values. That is why calculated using my regression analysis will approach as close as possible to y observed when the error is made a minimum. Theoretically, it should be 0. But that is never theoretic, is not possible out here. Okay, so here is a nice diagram of the regression line. So here I have data points out here. Okay, there is one data point and I'm drawing only one variable. In my previous equation I had 2 variables, but to make it very simple, let's have only one variable x out here. So for this molecule in my database, this is its x value, this is its y value. There is another molecule in my database. This is the x value, this is the y value. And so here I have, for simplicity, 1, 2, 3, 4, 5 molecules in my database. And you can see their endpoints are all varying out there. Okay, you can see this is the endpoint for this molecule, this is the endpoint for this molecule, and for our example, the endpoint is basically activity. This is the activity for the second molecule, this is the activity for the third molecule. So you have an activity spread, and I'm trying to develop a line basically of this type: y is equal to ax plus b, or put it c. C is the intercept. Okay, now there are several lines which I can draw. I can draw a blue line, okay, by regression, and I can draw a red line, and I can draw a red line by regression out here. So the question is now, which is the best line? Which is the best line that describes the best relationship between y and x for these 1, 2, 3, 4, 5 molecules, for these 5 data points in my data set? Is it the red line or is it the blue line that best describes the relationship between y and x? Okay, so now to answer this question, let's look at the error. So let's look at the blue regression line. Okay, this is the actual activity of my molecule, y experimental, and this is my model equation. Okay, the blue line is my model equation. According to my model equation, okay, what happens is, for molecule number 1, my model equation is saying that this is the activity, this is y calculated. So now you begin to see, now there is an error. This is the error. This is the error. Okay, so my model is actually predicting the activity much lower than the experimental or the observed activity. Now, if I were to look at the red regression line, if I were to see the red regression line, then the error, okay, according to the red regression line, predicts the activity even much lower. the red regression line. So there is a much larger error for the red regression line out here. So look at all of these lines. Look at the two lines and look at all of these points, and you can see for each one of these points you can see the error. Okay, the model error out here. So the answer is the blue line better or is the red line better? The answer lies in this. If I sum up the squares of all of these errors, okay, which gives me a smaller value? Okay, this square plus this square plus this square plus this square. There is no error for this point. Okay, is it smaller than this square plus this square plus this square plus this square? Is it much smaller? Okay, the one which gives me a smaller error, okay, the smaller square of the error is the preferable regression, line. So I hope you got this concept of regression. Regression is basically trying to minimize the error. The error should be the smallest out here. Okay, so if you're clear about this regression line, okay, then we can go ahead and actually see. So this is the concept behind regression, that I write an equation such a way that the equation, okay, represents the endpoints for each one of these molecules as close as possible to the experimentally observed value for these molecules. That is, the error between the calculated and the experimental is as small as possible. Theoretically should be 0, but theoretically never attainable out there. Okay, so now I'm going to teach you a little bit of mathematics now. Okay, so we are going to develop a regression line. What is our regression line? We want to develop this equation. Okay, so we basically want to develop this equation. Okay, so how do we calculate these coefficients A, B, and C such that these coefficients will give us the smallest value of the error? Okay, now one thing that I've never seen these days in any statistical class, exactly people actually tell you in a regression class how these coefficients are actually developed out here. From how do we get these coefficients? And I'm going to actually go through a little bit of mathematics. Bear with me, because this is not often found in many of the textbooks, exactly how this is done, how the coefficients are actually developed. Today we use software and you get all of these coefficients very automatically, but you must appreciate how the software actually develops your model, your model equation out there. And I'm going to show you how this is done out there. Okay, so you remember that basically what we're trying to find out, we are trying to find out a minimum in the error. And what is the minimum in the error? Is a minimum in the y observed minus the y calculated. This is y calculated. So y observed minus y calculated should be a minimum out here. So that is the function for which we are basically trying to minimize. Okay, why it is summation? Because this is for all the molecules that are there inside my database. So for all molecules, okay, the calculated y value and the observed y value, when it is squared, should be a minimum out here. And you know basically from mathematics that a function has a minimum when we differentiate the function with respect to the variables in that function out here. Okay, now let me go back and tell you what are the variables inside this function out here. Now this is slightly different. Now here is the mathematical variables that I am talking to about. Okay, okay, I said that these are the variables out here. Okay, in the sense that for different molecules we'll have, for example, one molecule will have a different log p value, another molecule will have a different log p value. Okay, one molecule will have a different HOMO value, another molecule will have a different HOMO value, and in that sense these are variables. These are the variables for the molecules in the data set. But now for my function, okay, What are the actual variables? The actual variables are the A and B and the C. I hope you get this concept very clear. For this equation which I'm trying to differentiate to get a minimum,
Yes,
I'm differentiate with respect to the variables. The variables here are A, B, and C. So please don't understand the variables for the molecules and the variables for this function which is being differentiated out here. Okay, so according to mathematics, if I differentiate this function with respect to A, okay, to the coefficient A, that should be equal to 0. That is the condition for a minimum. If I differentiate my function with respect to the variable B, I should equate it to 0. And if I differentiate the function with respect to the variable C and I equate it to 0, I will get these three equations. So those of you who know a little mathematics will get these three equations very, very, very easily. Okay. Now these three equations, okay, are slightly rearranged. Essentially, what is happening is this and this multiplied are put on this side. This and this multiplied put on this side. I've removed Y, the word observation, and only kept it as Y to make it very simple out there. Likewise, okay, this multiplied by N here is put it on this side out here. Okay, so I get a set of equations now from differentiation of my original equation out here. So I get three equations, E6, E7, and E8. Now I write them in matrix notation. Okay, I write them in matrix notation. So in matrix notation, basically those three equations are rewritten like this. Okay, and I want you to concentrate on this matrix. Okay, this is the matrix which has only the X variables. Okay, look at it. This is called the X matrix. It is a square matrix. Square matrix means the number of rows is equal to the number of columns. And it is a symmetrical matrix because if you look at the diagonal, you see on either side of the diagonal, we have the same elements. We have the same elements on the either side of the diagonal. That's why it is referred to as the square symmetrical matrix. Now I can find the inverse of this matrix, and this inverse of this matrix will get me another 3 by 3 matrix. This is also a 3 by 3 matrix, and when I invert it, I will get another 3 by 3 matrix with all numbers out here. Okay, with all some numbers out here. So I'm just calling this matrix as a C matrix. Okay, so I'll get some number here. That is C11. I'll get some number here, C12, C13, etc., etc. So I'll get these nine numbers, which I call it as the C matrix. I'm calling it the C matrix because I'll be utilizing the C matrix a little later on. Again, notice that the C matrix is again a square matrix, just like our original X matrix, and is also symmetrical, which means the coefficient C21 is equal to the coefficient C12. The coefficient C31 is equal to C13. Likewise, C32 is equal to C23. That is, it is a symmetrical matrix out here. Now, from this C matrix, actually we get our coefficients A, B, and C of our regression line. That from here, we'll actually get A, B, and C of our original equation. This A, B, and C of our model equation out here. And how we do that? We do that as follows. So A is equal to C11. Okay. Okay, A is equal to C11 into summation of X1y, okay, into this plus C12, this into this, okay, into this plus C13, this into this. So that is how I will get A. In a similar way, you can get B. So B will be obtained by multiplying this with this number with this number, this number with this number, and that is how I will get the coefficient B, my regression coefficient. And C likewise will be obtained by taking these three numbers and multiplying with these values in this column matrix. This is a column matrix out there. Okay, so that is how I get. And now I have my equation, my regression equation. A is equal to A x1 plus B x2 plus plus C. That is how the regression equation is obtained out here. Now, what I showed you here can be extended for any number of X. I can extend what I showed you. This mathematics is extensible for any number of X out here. Okay, so I can actually use the same mathematics to write this equation: ax1 plus bx2 plus cx3 plus dx4 plus a constant z. Okay, the same mathematics can be used to develop a more complicated regression equations out here. Of course, it will be a little more tedious. The size of the matrices will be a little larger. Okay, for example, if I have two variables, x1 and x2, then you can see I have a 3 by 3 matrix. So, okay, and if I have basically 3 variables, then I have a 4 by 4 matrix. So essentially the matrix will get a little larger, and they'll be a little more tougher to invert. Not very difficult actually, but all can be done in a computer in a jiffy out here. So I hope now this is clear to you. And now anytime somebody tells you about this regression methods and how the coefficients are obtained, please recall what I just explained to you out here. Okay, so once I have a regression equation, this regression equation is actually now backed up with a lot of statistical parameters. And the first statistical parameters that is shown on that comes from the regression is the correlation coefficient R. The correlation coefficient essentially tells you how good your model fits your experimental data. For example, it will tell you a measure of R will tell you whether this line is good or whether this line is good. That's how you will know whether this is a better regression line or that is a better regression line. You'll get an idea from R. So R actually is a measure of the quality of fit of the model. How good your model is able to explain the observed endpoints. How good is your calculated endpoints close to the observed endpoints out here. And now here is something which is very not often talked about. Okay, R can be expressed in several ways. R can be expressed as ESS divided by TSS. What is ESS? ESS is nothing but explained sum of squares divided by the total sum of squares. Or another measure for the correlation coefficient R is 1 minus RSS. What is RSS? Residual sum of squares divided by the total sum of squares out here. Now, these are the equations. Now, rather than showing you and talking to you about equations, let me show you by a picture what is ESS, TSS, and RSS out here. Okay, so here is a picture. I hope my screen is very clear to you. So on the y-axis, I have plotted all the compounds. Compound number 1. Okay, compound number 1 is essentially here. Compound number 2 is here. Sorry, this is compound number 3. Compound number 2 is here. Compound 3 is here. Compound 4 is here. 5, 6, 7. So a small database, a very small database of 7 compounds. And on this side, on the y-axis, I have actually plotted the log EC50 values of these 7 compounds, out here. And I have developed an equation. Okay, I have used my regression analysis and I have developed my equation. I have used that equation to go and back calculate it according to the equation what the exact value will be. So my regression equation tells me for compound number 1 that is actually its activity is 0.79. The observed activity is 1.07. My equation is telling me that the activity is 0.79. Okay, so now let me get out all of these writings. Okay. So now, okay, for my 7 compounds, okay, I have all different activities. For my 7 compounds, I have activity 1.07, okay, 0.09, 0.66, 1.42, minus 0.62, 0.64, and minus 0.46. These are the EC50 values of my 7 compounds. And according to if I take the average of these, 1.07 minus 0.09 plus 0.66 plus 1.42 plus this, if I take an average, this is the average activity of the 7 compounds. The average activity of the 7 compounds is 0.394 out here. Okay, so that is important. Okay, so Y bar, as you see in those equations, is basically your average activity of the molecules inside my data set. Okay, let me clear all these writings now. Okay, now this is according to my model. So the difference between the average activity and my model, that is 0.79 minus 0.394, is actually the explained sum of squares. Okay, the explained sum of squares for this molecule. The explained sum of squares for this molecule is basically this. 1.02 minus 0.394. The explained sum of squares for my other molecule, here this molecule is 1.26 minus 0.34. Okay, you have to square all of these numbers. So you got, what is the explained sum of squares? The explained sum of squares is the difference between the calculated values by the model and the average value of all the molecules in my data set. Okay, now what is total sum of squares? Okay, total sum of squares is actually, okay, the observed activity from the average activity. So the total sum of squares, that is TSS, is equal to 1.07 minus 0.394 the whole square. Again, for molecule number 2, it is minus 0.09 minus 0.394 the whole square. I hope you got this now. So it is the observed activity minus the average activity, the whole square, and summed up for all the 7 molecules. That is the total sum of, squares out there. Okay, now the residual sum of squares. Okay, the residual sum of squares is the difference between the observed activity and the calculated activity. The observed activity and the calculated activity squared up. Okay, so the residual sum of squares is 1.07 minus 0.79 the whole square. For this molecule, the residual sum of squares is 0.66 minus 1.02 the whole square. So I hope this is very clear to you. What is total sum of square? What is the residual sum of squares? And what is the explained sum of squares? So these are the values that actually help you to calculate the correlation coefficient. Okay, now the most important thing is this residual sum of squares. The residual sum of squares is actually the difference between the observed and the calculated activity according to the model. Of course, it is squared. I'm not saying squared every time, but please understand that is for all of these things, it is the square. Okay, it is the square of the differences, and this is the most important attribute which I'll be talking and using even later. The residual sum of squares, and I emphasize that it is between the Y observed, the difference between the Y observed and the Y calculated for each one of these molecules. That is the YI squared out there, and summed up for all the molecules is the residual sum of squares out here. Okay, so what is R square basically telling you? Telling us the goodness of fit, how close the calculated values are to the observed values. Okay, so when the calculated values are close to the observed values, we'll get a very high R square. Okay, if the calculated values exactly match the observed values, then the R square is equal to 1. When the calculated values are very, very different from the observed values, then the R square values will be very, very small, like 0.1 and 0.2, etc., etc. That tells you a very bad model. So good models will have correlation coefficients that approach 1. Okay, that approach to 1. Values above 0.9 tells you that you have built very good regression models out here. Okay, but should we be content in being happy that I have a model with a very good R square? No, we must be very worried of just R square. R square when taken alone can be very, very misleading. Very, very misleading, because I'm going to show you some this here. Okay, so here are some data points which are distributed out here, and you can see the regression lines for all these data points. Okay, and for all of these, the R square is about 0 for all these 1, 2, 3, 4, 5. For all of these 5 data sets, the R square is equal to 0.7, which is quite decent. And we could be very happy that we have developed very good equations out there. But sad to say, for other than for this, okay, all the other equations, okay, are inappropriate. For example, let's look at this. Okay, we have drawn a line. For all these data points, we have drawn a line. Is it appropriate? We have drawn a line with R square equal to 0.7. Is this correct? No. Because if you look at the data, we see that the data actually have a non-linear relationship. So we should not be fitting a line for these data points, but rather we should be fitting a curve for these data points. But anyway, foolishly, we have written a line, we have written this regression line, and a regression line gives us a very decent R square, and we are very content with it. We have explained our data points very, very appropriately. Wrong. We have developed a wrong model out here. So by just looking at the R square, we should be very worried with the R square out there, because there could be underlying different relationships out here. Look here. For all these data points, okay, for all these data points out here, we have developed a single line with an R square equal to 0.7. And we are very happy. We have explained the activity for all of these data points very nicely. Actually, wrong. Actually, there are 2 lines. We can write one regression line for these data points, and we can actually draw another regression line for these data points. So this data set actually has 2 regression lines, has 2 different behaviors. The molecules here cannot be explained by a single behavior. They are actually adopting 2 different characteristics or 2 different behaviors out here. And therefore, we must have 2 lines to explain their behaviors. Likewise, we can see here, this regression line is totally loaded by 1 point far away from the other cluster of points out here. So this is very inappropriate. Most likely, this will be an outlier. And we must take it out and then develop a regression for these set of points out here. Okay. Okay. So be careful with just using R square when you develop models out here. Another property which you should also look at is basically the standard deviation out here. Now, why the standard deviation is more important than R? Because it is an absolute measure of the quality of fit out here. Because as you can see, the standard deviation depends on the R square and also depends upon the degrees of freedom. N minus K minus 1 is the degrees of freedom. So what is N? Is the number of molecules in my data set for which I've developed the model. K is the number of variables that I've used to develop my models, X1, X2, X3. How many of these descriptors I've used to develop my model out here. So you see, S is a function not only of R square, it's also a function of basically of the degrees of freedom, the freedom out here. Okay, so S should be as small as possible out here. Now, what do I mean by as small as possible out here? Is 0.2 a good value to accept? Is 0.3 a good value to accept? Or should I look for a model where the S value is 0.1? There is no right answer. The correct answer lies in the structure of the database, the molecules inside the database. For example, if the standard error about the mean is 0.6, what do I mean by that? So for example, if I have 5 molecules with different activities, okay, with different activities, and this is the mean activity, and then I calculate, okay, the difference of all of these molecules from the mean activity, and then I recalculate the standard error for this. Let's say I get a standard error of 0.76. Okay, then I develop my regression equation, my model, and for that model, I have an S value out here. Now the S value is 0.28. Yes, now what happens is the S value for the model is actually much smaller than the standard error about the mean. Okay, the standard error of the mean is much higher than the S value that is calculated from the model out here. Now I can be very happy. And I say that I have developed a very good regression model. This gives me confidence out here. So along with R square, okay, we also need to look at S. And we need to look at what is the value of S subject to how is it in relation to the standard error of the molecules about the mean. When I look at that relationship, then only I can be satisfied and say whether my model is a good model or my bad model. Another thing out there, we must also look at the F value, the F test out here. Now, the F test, like the standard deviation, is also a function of the correlation coefficient and also of the degrees of freedom, also degrees of the freedom out there. So it is a very stringent test for the goodness of your model, or more appropriately, the statistical significance of your model out here. So do not neglect the F value. Okay, look at the F value and give it a careful consideration. Now, if you get a certain value, say F is equal to 29.5 out here, should you be happy that your model is good or your model is bad? What sense do I make of this value? So after I run my regression calculations using any software, the software will often give me an S value, which is calculated like this, out here. Okay, so what I must do, I must go to the tables, and this is very important. Listen very carefully. I must go to the tables and I must see for 95% confidence for confidence level. Okay, for these number of degrees of freedom, for n minus k number degrees of freedom for my data set. For example, if I'm modeling a data set of 30 molecules, 2 variables, then it is 30 minus 2 minus 1. K is basically the number of x's. That is 2 means that is x1 and x2. So my equation has basically x1 and x2. So that is basically k, the number of variables out here. So the degrees of freedom is 30 minus 2 minus 1 is basically 27. So I look in the tables, and for degrees of freedom 27, I look at the confidence value, and from the table some number will come out. Okay, let's say that that number is 7.38. Okay, now the statistics for my model, the F value for my model is 29.5. Now, the F value for my model is higher than that what comes from the table. The table gives me for these number of degrees of freedom, okay, it tells you at 95% confidence level that the value is, F value is 7.34. Now, my number is about approximately 4 times greater than 7. So if I multiply 4 into 7.38, I approximately get this value, okay, and I know that now, because the F value for my model is 4 times greater than that which is found in tables, I can now have confidence that my model is a statistically significant model out here. So when we develop a regression models, okay, don't be content with the R square. Don't just be content with the standard deviation S. Look at the F value. All these joined together will give you a confidence in how good your model. Only when these things are combined and taken together out here, then you can be satisfied that I have developed a very good regression models out here. Another thing that what I don't see these days, okay, many of the softwares don't actually report these days, is confidence intervals. Okay, so this is the A coefficient. So here are my 2 variables, x1 and x2. Okay, don't bother what these variables are. Some variables which are coded as NL and NC, don't bother about them. But I want you to concentrate on these coefficients A, B, and C, which I obtain by regression analysis. The mathematics that I just showed you, I use that mathematics to obtain these coefficients A, B, and C. How do I know that these coefficients are sound? How do I know that these coefficients are reliable out here? You can only see by looking at the confidence intervals. Okay, so what is the confidence intervals out here? So basically the confidence intervals for A is plus or minus 0.62. So that means actually it tells me that the A value can range from minus 3.14 plus 0.62. It can range up to minus 3.14 minus 0.62. 0.62. Why minus and plus here? Because this is a minus and plus here. This is the range. This is the range of my A values. Likewise, you can see the range of my B values, and likewise you can see the range of my C values, the C values out here. So look at these confidence intervals, and actually it is not difficult to determine these confidence intervals. The confidence intervals for these actually come from your C matrix. Okay, so the confidence intervals, okay, that I'm showing here, these numbers which with the blue arrows actually come from standard deviation multiplied by the student's t-test, student's t-value, multiplied by basically that C matrix, which I showed you, the diagonals of the C matrix. Let me go back. These diagonals of the C matrix, these values, C11, C22, and C33 are actually utilized in order to calculate your confidence intervals of the A, B, and C coefficients out here. Okay, so these confidence intervals actually should be very, very small. Theoretically, they should be very close to zero. Obviously, they'll never be very close to zero. If they are close to zero, that means you can say the A value is bang on minus 3.14. If the confidence interval here is zero, it means no that the B value is bang on minus 6.78 out here. But here we have the confidence intervals which show you the range for the B values. In essence, these confidence intervals should be as small as possible in relation to the coefficient values out here. Here you see basically, okay, the confidence interval is 25% of the coefficient. Look at this. The confidence interval is 25% of the interval. And therefore, do you think C has been determined with a good deal of confidence? Answer this question. Look at this confidence interval, look at the C value, and ask yourself this question. Do you think that the C value has been determined with a great deal of significance? I leave that answer to you out there. Okay, once we develop models out here, okay, we are happy with the R square, S value, F value out here, the confidence intervals for the coefficients out here. Something more important is basically the Q square or the R square CV. Now, often when we develop a model, what we want to use the model, we want to use the model for prediction. Okay, for example, I have developed a model for the activity and somebody says that, hello, Coutinho, I have a molecule here. Can you tell me whether this molecule will be active or not for this endpoint? Let's say I've developed a model for anti-cancer activity on some data set, okay, on some data set, and somebody comes up, Coutinho, I have a molecule here. Can you tell me whether this molecule will exhibit anti-cancer activity? And then I will use my QSAR model in order to be able to predict whether the molecule that this person is giving to me will be active, or how much it will be active as an anti-cancer agent out here. So this is the value for in modeling, that we want to use our models for prediction. But how can we have confidence that when I predict, that I'm not going to underestimate and I'm not going to overestimate my predicted values out here? So far, we have not seen anything about our models and how good our models are about the prediction out here. All that we have seen, R square, S, F value, and the confidence intervals are telling you the goodness of it. How good my model explains the observed activity. How good are the calculated activities in line with the observed activity. So just telling you about the goodness of it. Nothing, the S, the R square, the F, don't tell me about the confidence in my prediction out here. So in order to develop the confidence in my prediction, we have another matrix called the Q square, okay, or also variously called as the R square CV, cross-validated CV out here. So cross-validation is basically a technique that is used for prediction, for the prediction out here. Now, how is cross-validation done? So let's say I have a data set of 10 molecules. I have a data set of 10 molecules. What I'm going to do is basically I'm going to develop a model on this data set. Some model I'm going to develop on this data set. Then I trim this data set and I take out molecule 10. So I have another data set with molecules 1, 3, 4, 9. I've taken out molecule 10 and I've made a new data set with only 9 molecules. And I go back and do a regression and I make another model. Now remember that because you have taken out one molecule from the data set, this regression equation will be slightly different from this regression equation. So let me call this regression equation 1, and this is another regression equation 2 out here. E2 may be slightly different from E1 because there are only 9 molecules on which this regression equation has been trained. Now what I'm going to do is this regression equation, this model which I've developed, I'm going to use it to predict the activity of the 10th molecule. Okay, and I'm going to see how good it predicts the molecule for the 10th molecule. The 10th molecule was taken out from the database, kept aside for prediction. I'm going to repeat this now. Now this time what I'm going to do, I'm going to take out molecule number 9. So I 1, 2, 3, 4, 5, 6, 7, 8, and 10. Molecule 9 has been taken out from the data set. A new equation is developed, and I use this new equation basically to predict the activity of 9 out there. And I do all of these things. No, I keep on making these data sets, every time taking out one molecule, building a new model, and using that model to predict the activity of the molecule that was taken out from that data set out here. And then I compute this Q square value out here. Okay, the Q square value is actually given by this equation out here. Okay. Now what I'm going to say now, the Q square, like the R square, will turn out to be some number. You know that R square basically varies from 0 to 1. So Q square also will turn out to give you a value from. So Q square is basically given by all of these things that I've done. Okay, all of these things that I've done, a Q square value comes from all of these models that I've developed. Several hundreds of these molecules I would have developed. Every time taking out some molecules, leaving them aside, and predicting their activity out there. And from that, I can calculate a Q square using this equation out here. Now, we must note that Q square will always be lower than R square. So if R square is about 0.9, when I do this exercise of cross validation, I may get a Q square is equal to 0.6. Okay, so just like R square is equal to 0.9 means 90% of the molecules in my data set have been correctly predicted. Sorry, have been correctly fitted. Sorry. 90% of the molecules in my data set have been correctly fitted by the regression line. Q square tells me basically that 60% of the molecules have been correctly predicted. Okay, that means 40% of the molecules, their predictions have been in error. So should I be happy or not? Should I be happy or not with this value? So this is the goodness of fit. 90% of the molecules have fitted well in the model. 60% of the molecules their activities have been predicted well. 40% of the molecules the activity have not predicted well. Should I be satisfied with this model or not out there? Okay. The answer to this is in the next slide. Okay, so let me repeat. Okay, I'll tell you now about the Q square value. How good should I be? As I told you, Q square value, it should approach to 1. A good model will have a Q square value as close to 1 as possible. Sorry, R square. Sorry. R square value will be as close. A good model will have an R square value close to 1. What should be a good Q square value for a model? What is a good Q square value for a model? Okay, remember that R square is goodness of it and Q square is goodness of prediction out here. So you would obviously tell me that, okay, Q square should be able to predict the activity of all the molecules very, very well. And like R square, Q square should approach to 1. Okay, but this practically never happens. Usually Q square is always much smaller than R square. Now think about this and ask yourself this question: why is Q square always smaller than R square? So if I have a model which R square is equal to 0.95, generally the Q square will turn out to be 0.7. Okay, it'll always be smaller than this one. In fact, if your Q square approaches R square, if you get a Q square that approaches R square, you should be very suspect of your model out here. What does it signify? A Q square that is very, very high and very close to the R square tells you that your database has a lot of redundancies. I repeat this. When you develop a model and you get a Q square value, a cross-validated correlation coefficient that is very, very high and that is very, very close to the R square value. For example, if you get a Q square value of about 0.9 and an R square value of 0.95, I would be very skeptical about your model out here. I would reject this model. It is simply because the data set that you have used to develop a model has a lot of redundancies. A lot of redundancies means that there are very, very similar molecules inside your data set, and therefore it is not surprising that when you leave out molecules from your data set out here, okay, there is nothing better than to predict out here. There is no basically what I would say, a task to predict out here. There's not a great task to predict out here. It's easy to predict out here because the molecules that you have taken out from here have a representative already inside in which you have developed your model out here. So that means the molecules that you have taken out are not very much different from the molecules that are already present inside your database out here. That is the meaning of redundancies, a lot of similarities in your data sets. And therefore, what would I do? If I come across such things, I would go back and look at my data set very carefully, and I would actually do a lot of similarity searching about the molecules and weed out the molecules that are very similar. So I would go back and prune my data set and take out very, very similar molecules and restart all the exercise all over again. So in general, I would say that your Q square values must be about R square minus 0.3. That is a good model. Okay, so a good model has a Q square which is 0.3 less than the R square value. So if your R square is 0.95, okay, if your R square is 0.95, then a good Q square is basically 0.65. This is a very good model. Okay, now I know some of you are thinking, oh, only 65% of the molecules are predicted well. It is good. It is good. Okay, I would push this up to 0.7. Okay, but beyond that, then there is a lot of susceptibility about the type of molecules that are there inside your database out here. I'll skip about bootstrapping out here. I'll come to some aspect about number of variables out here. Many times in regression, we would like to develop an equation ax1 plus bx2 plus c. Somebody will ask, hey, why not develop another equation with ax1 plus bx2 plus cx3 plus d? Why not develop this equation with 1, 2, 3 variables? Why are you satisfied with an equation with only 2 variables? Why not add another variable out here? The answer is this. Then I can still add. Why not develop another equation with 4 variables? Would not that be better? Would not this equation be better than equation, and this equation is better than there is no end to the number of variables that we can go and add to develop a regression equation. One thing that you must remember, whenever we add a new variable, we can always improve the R square. Okay, so that is the trick. A lot of people, when they want to improve the R square for their models, they keep on adding a new variable. So adding a new variable now, my R square will go up. Okay, for example, with 2 variables, if my R square was 0.9, with 3 variables, my R square will go to 0.93. With 4 variables, my R square will go to 0.95. And you might be thinking, hey, I'm getting better models because R square is approaching 1 out here. No, but you're fooling yourself out here. Okay, so if I have to make a choice between an equation with 2 variables and a model with 3 variables, which one is better? The test for this is called the sequential F test. Okay, so I calculate the sequential F test. For my first model with 2 variables, I calculate the R square. For my second model with 3 variables, I calculate the R square. And then I know this. Okay, the number of degrees of freedom, the difference in the variables. Okay, so this will be 3 minus 2. There are 3 in my second equation and 2 in my first equation. And I calculate what is called as a sequential partial F test. Only when this number, okay, indicates a 95% significance value, can I justify that the 3 equation is to be preferred over the 2 equation. The 3 variable equation is to be preferred over the 2 variable equation out here. Only if the F value has a significance, only if the F value has a 95% significance, can it justify that the regression equation with 3 variables is preferred over the regression equation with 2 variables out here. So that is how we know how many number of variables we need to add to our models out here. Okay.
Sir.
Yes.
Sir, in the previous slide, the upper part n minus k, in that k, what we have
First
to
model.
take?
First model. K is for the first model. Number of degrees for the first model.
First model.
Yeah.
If
So the number
first model is for 2 variables,
two
then
variables.
it will be
2 variables. Then n minus k is for 2 variables.
Okay.
For the numerator. Okay. For the numerator is for the smaller number of variables in my model out here.
Okay.
Okay. So because what will happen, we are all tempted. I am also tempted to make regression equations with 10 variables, with 12 variables out. There is no end. Because cunningly, I know that if I add the number of variables, I can artificially shoot up the R square and I can get a good paper. Then I can tell the referee, see, my R square is 0.98. I've got a very good model. But then, we are all fooling ourselves because we know from statistics that more the number of variables, the R square is bound to shoot up. Okay, that is the law of the statistics out here. But then you are also going to happen something. More the number of variables, you'll have other problems which will come in. Sometimes the predictability will go down. The Q square will go down. The R square CV will go down out here. Okay, so be careful in just being greedy and just adding number of variables inside your model out here. I want to talk to you something about model validation out here. Okay, and this is very important. Today, everybody talks about validating. Whatever we do, they say, do validate your model. Is your model actually validated out here? So today, a lot of papers are recommending that we do model validation. All that I told you are requisites, important out thing. But another thing that papers today, that journals today are asking for to do model validation. And there are several methods for model validation. There is the Matthews correlation coefficient. There is the overall accuracy of prediction, and there is sensitivity and specificity. And I'm going to talk about these 2 aspects, sensitivity and specificity out here. And let me talk in the current context in COVID too. Okay, in COVID-19. In COVID-19, we have several tests that are going on. For example, there is the antigen test, and there is basically the PCR, the PCR test out here. We know that the antigen test is basically not sensitive, and neither it is very, 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 very specific out here. It's a very unreliable test. If the test shows that you are negative out here, you cannot go with the hope, with the this in your heart that, oh, I am not COVID-19 positive. No, many people who have been tested COVID-19 negative in this antigen test, actually by the PCR test, they have found to be COVID-19 positive out here. So this sensitivity and specificity are very, very important today. Okay, so for my regression models, how do I calculate sensitivity and specificity? Now, what is sensitivity and specificity in terms of our regression models out here? So many times our models, what they are doing is the active molecules, they are predicting as inactive. This is very bad. If my model predicts an active molecule as inactive, I have a very poor model. Worse is when inactive molecules are predicted as active. Very hilariously, if somebody who is not COVID-19 positive, actually it turns out to be that the test says that he is COVID-19 positive. What a sad thing it would be. You would be dumped into the hospital and tied up in chains, and what a horrible thing you would undergo. Right? If I had a test today that all those who are not COVID-19 positive turn out to be active according to the test, it would be such a horrible situation, Think of the trauma it would cause to the patient and to his family members out here. Okay, so I do not know which one is the devil. if a model predicts the active as inactive, is that this, or the worst devil is that if a model predicts inactive as active, which is a lesser devil or the greater devil? Hello? Hello?
First one.
First one, I say the second one. I think the second one is the worst devil, that inactive people are turned out to be active. Okay, so this is about sensitivity and specificity. Models that are predicting active molecules as inactive, and specificity is models that are predicting inactive as active out there. Okay, how do we calculate? So these are the two equations that you have to calculate for sensitivity and specificity. So today, when you are developing models, all journals will demand that you actually show the sensitivity and the specificity for your models, basically telling you, like, for example, sensitivity is the number of true positive divided by the number of true positive and false negative. Okay, and false negative out here. Okay, so you'll see that sensitivity is always going to be less than 1. Okay, specificity, true negatives divided by true negatives plus false positives for false positive out here. Okay, so if this is 0 and this is 0, then sensitivity will be equal to 1 and specificity will be equal to 1. But of course, they will never be the same. We should try to see that our models get sensitivity and specificity as close to these values as possible, so that there are none false negatives, neither there are false positive for the false positive out here. Okay, so very easy to do that. You know, basically how many false negatives and false positives will be there. Okay, you know that exactly for the set of molecules. After you develop your model, you know how good your model is behaving, how good it is predicting out here, and you can use those numbers to calculate your sensitivity and specificity out here. Besides this, several other metrics today journals are recommending in order to
Sorry.
Yeah.
Sir, for sensitivity and specificity, I have seen many papers are giving something called as ROC curve.
Yes. You can do the ROC curves also.
Okay.
Yeah.
Okay. Fine.
This is mostly coming from Matthews CC.
Okay.
Matthews correlation coefficient. This is coming from Matthews. This is related to ROC curves. Yes, if you can plot the ROC curves also, it is very, very good. The diagonal of the you have to get far away from the diagonal of the ROC curve on there. You know that, right? Okay, so you can do that also today. Okay, but this is coming from Matthews correlation coefficient, sensitivity and specificity out there. Okay. Yes, you can go ahead. Okay, so another thing that journals are recommending today is for your models to calculate the R square M and the R square P value. So this is the equation for the R square M. Okay, so this is the R square for your model. And R square 0 basically is when the C coefficient is set to 0. So what is our model? Our model is equal to AX1 plus BX2 plus C. So R square is for this model. R square naught is when you have your model is equal to AX1 plus BX2. I do not have C here. That is basically, okay, in the first case, the line has an intercept. Okay, this line has an intercept. This is the C value. This line is basically going through the origin. This line is going through the origin. So this line has R square, and this line will basically have R square equal to 0, where you have forced the regression line. We have forced the regression line to go through the origin 0, 0. That is, and you can easily calculate the R square and the R naught square. The software will calculate for you out there. Okay, so when you use this calculation, if you get an R square M greater than 0.5, you know that it's a good indicator of external predictivity. What do I mean by external predictivity? Remember that we develop models for a given database, for some molecules inside a database. If I have a molecule that is outside the database, a molecule that is different from the database, and when I use my regression line to predict the activity of this molecule, which was not inside the original database for the training out here, this R square M value will tell you your confidence, how good you are able to predict a molecule that is outside of the training database out here. And if you get an R square M model greater than 0.5, you can be happy that your prediction will be quite good. Now, why R square M is important? Because R square M is actually developed on both the test set and the training set. Okay, so the test set is often used to get R square. Okay, the training set. The test set is often used to get R square pred. Okay, often you know that when you have a database, okay, and you do model development, what you do is you bifurcate the database 2/3 for training, and you keep 1/3 of the molecules, okay, for testing out here. And this R square pred is basically developed only on this 1/3 molecules out here. So it's a very small number of molecules on which R square pred has been developed, has been calculated out here. Okay, now R square M is better than R square pred because R square M uses both, uses the entire data set, uses both 2/3 plus 1/3, use both the test and the training set in order to do its calculation. That is why R square M is a much better matrix than the R square pred, and that is why it's a much better matrix for prediction than the R square pred. So if you want to have confidence in your predictions, in your model's prediction, please use R square M rather than R square pred for your predictions out here. Another model which journals have been recommending this day is another matrix called the R square P. The R square P is an indicator of model acceptability out here. Now, what is the R square P? The R square P is coming from the R square. Okay, I've written capital R square. Always I've been writing as small R square. It is the same. Okay, it is the same. Okay, so it is coming from R square, plus it is coming from another R square R. What is R square R? Now let me tell you what is R square R. R square R is a randomized model out here. So what is randomized model? So if I have my database, okay, molecule number, if I have molecule number 1, I have activity A1. Molecule number 2, I have activity A2. Molecule number 3, I have activity. So for all these molecules, I have their activities. These are the observed activities out here. Now, in a randomized database, what I'm going to do is, for molecule number 1, I'm going to give it activity 3. Activity 3 now is ascribed to molecule number 1. Molecule number 2, the activity is given of molecule number 10. Activity of molecule number 10 is ascribed to 2 out there. So what you begin to do, you shuffle the activities and the molecules out here. So originally, molecule number 1 had activity A1, that was the observed activity, the true activity. Now I'm giving it some fictitious activity. I'm giving the activity of molecule number 3 to A1. Okay, some wrong activity I'm giving. This is called a randomized data set. And now when I try to model, when I try to develop a model for this randomized molecule, you know, obviously the model should be a very poor model, because, you know, the molecules have been given all wrong activity values. So very obviously the R square for such a model should come to very close to 0. But it will not come to 0. It will come to some small value. It should come to some small value of 0.1 or 0.2. So that is what is called as R square R. When the database has been randomized and you recalculate a model and you recalculate the R square, this is the R square that you should be reporting as the R square R. So when you do this, okay, for the original model, for the randomized model, when you do this calculation, okay, you'll get an R square P value, and this R square P value, if it is greater than 0.5, you have a very good model acceptability. So what I'm trying to emphasize now, almost for the last 1.5 hours, is matrices, which are important in regression. Give a lot of attention to these matrices out here. Then only you can satisfy yourself and have the confidence that you are going to basically do We built a very good model out here. Okay, so I think Dr. Sandesh is going to talk about principal component analysis tomorrow, and I'm going to skip this. Okay, I'm going to skip this about this out here. Okay, I have a lot to talk about. I thought I could talk about a lot in 1.5 hours, but very sad. You know, I thought I would like to talk about linear discriminant analysis. I would like to talk about the KNN algorithm. And more importantly, I would have loved to talk about neural networks. You know, neural networks today are the backbone of what everybody is hyping about. Machine learning and artificial intelligence, the backbone of all of these things, what is being hyped a lot today. Every second day, there is a seminar, a conference, a meeting, and people are talking about this, about artificial intelligence and machine learning. The backbone of all of these things today, okay, the modern methods is basically this neural networks. However, sadly now it is 3:30, and I know some of y'all are very, very bored about listening to this lecture. I would have loved to talk about neural networks, but I'll have to skip about neural networks. Okay, so Dr. Sandesh, are you there, Dr. Sandesh Loda?
Sir, Bhavin here. Tell me.
Dr. Sandesh is going to talk tomorrow about principal component analysis.
Yes, sir.
Okay,
sir,
so
I am going to talk principal component analysis, but
okay.
I had decided to go by calculating eigenvector and eigenvalues.
Great,
so
great.
Nothing like what I can see on your slide. I'm not going to explain that, but I'm trying that I can able them to calculate how to calculate eigenvector and eigenvalues.
Great, that is all. So can I ask you something? Can you extend your lectures to PLS? Because what happens, partial least squares is very similar to PCA.
Yes, sir.
Okay, so if you can extend your lectures to PLS, then I think they will appreciate PLS also. Also a little.
Sir, actually, I have planned that I explain that theory part, and I using two software how to do that I am going to show them using SPSS and Origin Pro.
Great. So if you have time, can you tell them about PLS? Because PLS is now also a very important, one of the very important regression chemometric methods, partial least square. Okay,
Sure,
turning
sir.
out to be very important. Okay, so now I think my time is up. I do not know. I would love to do all of these things, you know, talk
Sir,
to you about
if we
discriminant.
have time, if you can explain any one method, it will be fine.
Okay, so I'll talk about neural networks. Okay. Hello.
Yes, sir.
Now, I'm not an expert in neural networks. Okay. It is the domain of computer science. So I'm in no way any close to the engineers. Okay. But what I'm trying to do as a pharmacist, how I understand neural networks and how is it important, not only in chemistry. You pharmaceutics people, you know, I'm going to show you that neural networks have been used even in pharmaceutics. Please look at this. Neural networks have been used in pharmaceutics for pre-formulation studies. Okay, for example, people have used neural networks to predict drug intrinsic solubility. People have used neural networks to understand formulation of immediate release IR tablets. People have used neural networks to optimize a tablet formulation. People have used neural networks to optimize tablet coating. People have used neural networks to optimize freeze drying, mucoadhesive system for vaginal delivery of the drug. People have used neural networks to design controlled release formulations out here. So you can see the power today of artificial neural networks. Okay, so it is not only a domain in chemistry where we are trying to model pharmacodynamics, model pharmacokinetics, volume of distributions, clearance, Cmax, half-life. or we are trying to model toxicity, or we are trying to model metabolism. It's not only limited to this. You know, people are using neural networks even for pattern recognition, for speech recognition. In fact, it is used today so much when we talk to Google, okay, Siri, or when you use Cortana. Basically, when we talk to Cortana, we talk to Siri on our mobiles, basically, we are using artificial neural networks. That is how they recognize our voice and able to give us responses out here. Okay, so it is very ubiquitous. Okay, so the neural network is actually very, very, very ubiquitous, being used a lot in many, many places in physics, in chemistry, in biology. And I want to say that it has even invaded pharmacy. And all, whether it is pharmacology or chemistry or pharmaceutics, today neural networks have been used a lot to explain a lot of the problems in our pharmacy area out here. Okay, now it is very, very highly mathematical. The neural network is very, very, the operation of the neural network, the construction of the neural network is very, very mathematical out here. And just like you, I'm not a very mathematics oriented person out here, and I must very honest that I don't understand it fully well. Okay, I'm struggling to understand it. We are going to start implementing it, but we are struggling to implement it also. I will tell you a little bit and give you a flavor of what actually is artificial neural networks. Okay, just that. Okay. So this is your biological neuron out here. Okay. So these are the dendrites, these are the nucleus, this is the axon, and this neuron is connected to the other neurons. Okay, with their own, this is the dendrites of another neurons, this is your synapse out here. So this neuron receives information from another neuron, processes this information, and sends out this information to somewhere, to an effector system, maybe to a muscle, and the muscle will contract. The muscle will contract out here. Okay, so this is a biological neuron out here. The computational neuron is actually shown by this. Okay, this is a neuron which receives input from the other neurons. Okay, it analyzes the information. Okay, does some calculation and sends out some signal, and sends out some basically signal out here. Okay, so this is the construction of a biological neurons, and you can basically see how it closely resembles. Sorry, this is the construction of the artificial neuron or the computational neuron, and how it closely resembles the biological neuron. Now, to make an ANN, actually we have to assemble these neurons in a network. Okay, the full network is composed of several layers: an input layer, an output layer, and an hidden layer out here. So this is how it looks. Okay, so this is the input layer of neurons, this is the hidden layer of neurons, and this is the output layer of neurons out here. So these are some neurons, okay, in the input layer. These neurons will receive information. So as you can see, it is the information received by the neurons in the input layer is then transmitted to the neurons in the hidden layer. These neurons in the hidden layer will do some computation, will do some calculation, and will send an output to the neuron in the output layer, where you get the output Y. So from the axis, the input axis, basically by passing through these neurons in the three layers, you get an output Y. So let me explain why. Let's say for our sake it is activity. It could be anything, as we have seen. It could be any of the pharmaceutics thing that I just showed you. It could be any of the pharmacodynamics thing. Y could be any of the endpoints out here. And what is basically X? X is the input variables. This is the same that I was talking to you about in my regression. This X1 could be log P. This could be HOMO energy. This could be polarizability. This could be dipole moment, etc., out here. So what I'm trying to do is basically, I'm trying to model the activity of a molecule through this network. Okay, through this network, I'm actually trying to model the activity of my molecule through this network, which is a compilation of neurons in the input layer, in the hidden layer, and in the output layer. So the input layer is basically a layer which only receives information and distributes it to the hidden layer. The hidden layer is basically which does the computation. After the computation is done, basically it is sent into the output layer. The final answer that is given out, it is given to the output layer. So this is the construction of a artificial neural network. Now, how many neurons are there in the input layer? How many neurons are there in the hidden layer? So here you can see basically there are two hidden layers. There could be more than two hidden layers. Mostly for chemistry, we use only one hidden layer. One hidden layer is sufficient. Okay, the number of hidden layers to be used depends upon the complexity of the problem, the number of molecules in the data set, the targets that we are trying to model, the Ys that we are trying to model, all depend upon how many hidden layers that we have. And how many neurons are there in the hidden layer is as follows. So let's look about this. Okay, how many neurons should be there in each layer? So in this figure, we have seen basically 1, 2, 3, 4 neurons that are there inside the input layer. The rule is as follows. The number of neurons in any layer is directly dependent on the number of variables. So here basically, as you can see, I'm using 4 variables to develop my endpoint. That in this case, first, let us always say it is activity, but it could be anything. It could be a pharmaceutics problem. Okay, it could be a pharmaceutics problem of optimization of your dosage form. It could be anything. It could be a chemistry problem like activity, a pharmacokinetics problem, etc., out here. So I'm using basically 4 variables, as I said, log p homer, in order to model my endpoint. So the number, if I'm using 4 variables, there'll be 4 neurons in the input layer out here. Okay, so the number of neurons in the input layer is directly on the disk. Okay, the output. How many neurons are there in the output? Normally, we'll only have 1 neuron inside the output. I've seen also output with 2 neurons also. Okay, for example, where will I use 2 neurons? If you were trying to predict, for example, selectivity, alpha 1 for your molecules, alpha 1 versus alpha 2 selectivity, or beta 1 versus beta 2 selectivity, something you're trying to actually model selectivity. In this case, I'm just trying to model only activity, so it suffices me to have just 1 neuron in the output layer. So you can have as many number of neurons in the output layer, as many as your targets out there. For example, you wanted to model Cmax and volume of distribution. Maybe you can do both with 2 neurons in the output layer out here. But most of the time in chemistry and in pharmaceutics, we will restrict ourselves to just modeling 1 endpoint at a time out there. Okay, so go back. So the number of neurons in the output layer is directly dependent upon the target that we are going up. Now, how many neurons are there inside a hidden layer? Okay, obviously, how many number of hidden layers that we'll have will depend upon the complexity of the problem, the size of the database, the complexity of the problem that we are trying to do. For example, if you are trying to do speech recognition, okay, you are trying to do speech recognition, then often people use a large number of hidden layers in order to do speech recognition out here. Okay, so if we use one hidden layer, if we use only one hidden layer, and this is most of the time in chemistry and in pharmaceutics, the number of neurons in the hidden layers, okay, will be equal to or slightly more than the number of neurons in the input layer. As you can see here, 1, 2, 3, 4, 5. I have 5 neurons in my hidden layer, while I have only 4 neurons in my input layer. So the number of neurons in my hidden layer can be equal to the number of neurons in my input layer, or many times it can be greater than. Okay, it can be greater than the number of neurons in the input layer. Often it is greater than the number of neurons in the input layer out here. Okay, so now what is done? Okay, so the input layers are basically, the neurons in the input layers are basically distribution out there. Okay, so let me clear this. Okay, so what the neurons in the input layer take some information and then it distributes it to the neurons, and then it just distributes the information to the neurons in the hidden layer. Look at this here. The information here is distributed here. Okay, so from each of the input neurons, information is going to each one of the neurons in the hidden layer. Okay, information from here is going to all the neurons here. Information from this neuron is going to all the neurons, as you can see these lines. Okay. Okay, so now how much of information, for example, let's look at this. Now I'm taking some information here. For example, this is a log p value and some value log p is equal to 2.5. This value is actually going to be distributed to this neuron. Some value is going to go here, some value is going to go here, some value is going to go here, and some other value is going to go here. How much goes here is called as the weights. The weights. Okay, so J is a neuron or a node in the hidden layer, and I is a neuron or a node in the input layer. So these are the weights. How much of 2.5 will be distributed to 1? How much will go to this? These are basically the weights out here. Okay, so now all these weights have got to be adjusted in such a way. Okay, all these weights, this weight, this weight, this weight, this weight, this weight, this weight, all these weights, okay, that information that is being passed from each of the input nodes into the hidden nodes has to be done in such a way such that my target endpoint, that is which I'm actually going to calculate by this neural network, should be as close to the observed. That means my error should be equal to 1. So that is the whole trick. The whole trick in the artificial neural network is to adjust these weights. Such that after it is processed out here, the end value should be as close as possible to the observed value out here. So I emphasize that. So the artificial neural network is nothing but adjusting these weights, all these weights inside out, okay, all these weights that go from here, even that weights that go from this to here to the endpoint, to adjust these weights such that y calculated is as close as this out here. So so let me tell you what is being done. So the first thing is that we have to train the artificial neural network. So we have a set of molecules for which we know the variables, and for each molecule we know what is the endpoint, the activity out there. Okay, so we'll present to the artificial neural network a set of molecules, maybe 30, 40, whatever molecules we have from our database, 100 or even 1,000 or even lakhs out of this. We can train our molecules in such a way that there is a good prediction of the activity out there. So that is called the training part out here. And in the training part, what is happening is that these weights are being adjusted such that, okay, that for all of the molecules, y calculated is as close as possible to y observed, that the error is as small as possible out here. So let me go back and tell you out here. Okay. Now there is something else also, which is also there. Okay. Every layer has a bias neuron. Okay, has a bias neuron out here. Now, why this bias neuron is there out there? Okay, we know that y calculated should be as close to y observed out here. Okay, in order to do this, sometimes we need this bias in order to pull this as close as possible to the y observed out here. Sometimes just with these x's, it is not possible to get y calculated as close to y observed as possible. So therefore, we utilize this bias in order to be able to do this fulfillment out there. Okay, so there is a okay. So that is about this bias neuron out here, and I hope you appreciated the bias neuron. Okay, so here is a little mathematics of how the information is transmitted to each one of these neurons. The input that goes into each one of these neurons is actually given by, okay, the weights coming from the previous neuron into the output of the previous neuron out here. Okay, I'm not going to talk about all of these things out here. Okay, the most important thing I want to tell you is this processing which goes on. Okay, this processing is basically transmits information from here to the output layer, and this processing is very important out here. So this processing layer actually processes information in a very odd way. Okay, the processing, the output that comes from every neuron is actually given by this function, which is called as a squash function. It's called a squash function. So actually it takes the input, okay, and the output is actually a function of the exponent of the input, e raised to minus input out here. And the squash function has different types of squash function. One type of squash function is this sigmoidal function out here. Okay, so what is happening is the processing. Okay, if you look at this function, basically this is a non-linear function. Okay, so basically, let me go back. So from the input, the output from a node. Okay, so let me go back. The output from a node, this is the input that is coming to a node or a neuron. Okay, the neuron is processing something and it's sending some information, outside. This processing is given by this equation. Okay, so how is it taking all this information and how is it processing it to process this output is given by this equation, and this equation is basically a non-linear equation. So what it can actually do is, okay, let me take out what it actually can do. It actually can convert linearity into non-linearity. Okay, so that processing function, that squash function, converts linear input into non-linear output out here. That's all that I want to say. That's all that I want to say about this equation. The wonder of this equation is to take a linear input and convert it into a non-linear output out here. Now, why do we want to do this out here? Because many times, okay, we see that, okay, the relationship between an endpoint and the variables, many times this relationship is a non-linear relationship. Now let me explain to you. Now, when I wrote this equation, y is equal to ax1 plus bx2 plus c, this is a linear relationship between y and the variables out here. But many times the endpoints are much more complicated, that a linear relationship is not satisfactory. For example, if y is, for example, volume of distribution, then very likely volume of distribution is actually a non-linear function of these variables out here. Okay, so I cannot model volume of distribution by the simple linear relationship. I need non-linear. And what do I mean by non-linear relationship? A non-linear relationship may be like this way. This is a non-linear relationship. Okay, or a non-linear relationship may be of this type. Got it? Okay, so many times Y needs these type of terms in order to get the relationship. We need these type of terms between to get these non-linear terms. We need these non-linear terms in order to develop a good equation. So all the equations that I was showing you about linear relationships sometimes do not give us good models out here. And many times when you do not get good models with these type of equations, think about developing non-linear relationship. But I warn you that you must be sure that there is a non-linear relationship that exists for your target function. If you're not confident that there is a non-linear relationship, then simply don't develop non-linear models out here. Okay, but the power of ANN is to let you develop non-linear, is to develop non-linear models out here. Okay, I know there is a lot to talk about the construction, about the errors, how the error is back propagated. Okay, how the neural network learns finally and develops a good Y equation out here. There's a lot to talk about out here. There's a lot to talk about feed forward, back propagation, neural networks. How is the error back propagated into the network so that the error is minimized out here? Okay, there's a lot to talk about, but I think you're all getting bored, and I will stop at this point of time and just tell you that the neural network today is the backbone of machine learning algorithms out here, and it is being widely used in all domains in pharmacy, whether it is chemistry or pharmaceutics or pharmacology out here. To understand a lot of our problems in pharmacy, people are using neural networks, okay, to do this. Okay, so thank you. I'm sorry if this was very, very mathematical, but I hope those of you who are venturing into making models and developing models would have learned something from this talk. So thank you very, very much.
Thank you very much, sir, for your time and explanation of equation. Explanation of equation is also required because nowadays we, based on using software, and we don't know what is going behind that software. So actually, we, being a teacher, we should know what exactly it is going backside of that software. So these equations are important. Thank you very much, sir, for spending giving us your time. As a gratitude, I'll be sharing you e-certificate. So as a gratitude, please accept this e-certificate. Once again, thank you very much, sir, for your knowledge sharing. It is always very, I can say, we will be on the toe of a chair when you teach everything regarding QSAR or regarding this regression also. And I'll try that tomorrow. I'll be at your level, trying to achieve your level in explanation of principal component analysis.
Please do.
Majorly, I'll be focusing on parting on machine learning as well as your regression part.
Thank you. Good. Thank you. Nice. I'm very happy that you can take it forward, and students and all our teachers will appreciate that. Thank you so much. Thank you for this invitation. Thank you both, Dr. Bhavin and Dr. Sandesh, for this. It was nice interacting with you all once again. Thank you and bye.
Bye. Thank you. Thank you, sir. So dear participant, we have finished the fourth day. So this was the end of our fourth day. Tomorrow we'll be again meeting at 10 a.m. sharp. We will be having only 2 sessions followed by yoga session. And tomorrow we'll be also having exam, what you have learned. So we'll be floating a Google Doc form There will be MCQ, mostly of 15 marks. Everybody has to clear that, then you will be getting a certificate that is mandatory from AICT side. So we'll be floating MCQ based on the lectures what you have attended in that 5 days. And after my lectures tomorrow, we'll also have some interaction that you will be interacting with each other by giving your name, designation, and from where you are coming, and what are your interest, research interests. We'll be also having that session tomorrow morning only. So thank you once again. We'll meet again tomorrow. Thank you. Thank you very much.